Let me start that up. We are recording. All right. So let me pull out my notes as a whole bunch of people are piling in. So this is the first of a session, a bunch of sessions we'd like to do with guests as hosted by the Cybersecurity Master's Program as part of the Tecnológico de Monterrey Engineering School, Engineering and Science School, for don't want to forget about my colleagues in science. And I really want to thank Brian Delgado for joining us. Brian was a contact through one of our students of the Tec de Monterrey, Maggie Juarez, who was a student here in Guadalajara, graduated back in about 2009 and is now working at Intel up there in Portland with Brian, and put us in contact with Brian, and he wanted to share with us and get in contact with students with us. So I'm really happy to have him. Brian is a security researcher at Intel Corp, focusing on firmware security and fuzz testing. Brian did complete his PhD at Portland State University in the area of firmware-based rootkit detection, and he has published papers on performance measurement, firmware security, and rootkit detection. So without any other formalities, I'd like to invite Brian, and thank you so much for joining us this evening.
Thanks, Ken. I'm glad to be here. Hello, everybody. I'll be talking tonight about fuzzing and how we can find security issues automatically using more advanced software techniques. So I work for Intel, and I think because a lot of you are college students, Ken was interested in me sharing a little bit about my background too, so I can do that. So I'm the red team lead for one of the business groups at Intel called Programmable Solutions Group. And our business group, we create FPGAs and ASICs and other accelerators. And our role for the red team is to try to find security vulnerabilities in those devices before they leave Intel. So we're actually very happy if we're able to find some security issues before it makes it out the door. So my personal interests are very much in the intersection of security and performance. Anytime that there's a security mechanism, there's often a performance overhead for that. And so I'm very interested in sort of poking at that boundary and better understanding the trade-offs of additional security versus reduced performance. I've also spent a number of years working on what are called supervisor operating modes on the x86 processor. So on Intel, we have the system management mode, which is a very highly privileged supervisor mode on the system. And that's basically what operates the runtime BIOS on your system. And to better guard the operating system and hypervisor from potentially malicious BIOS code, we helped design the Intel SMI transfer monitor, which is a way to apply a protection policy over what your BIOS is allowed to access on your platform. I'll be talking a lot about fuzzing tonight. That's the main focus. I've also spent a number of years working on virtualization. So my academic background, as Ken mentioned, I finished my PhD last year after, I think, 9 years of part-time work. It was a project called EPA-RIM, and the idea was that we could use firmware to detect rootkits in operating systems or hypervisors. And we were leveraging that very privileged mode called system management mode, which basically gives you full access to the memory and registers of the system. So we could go do things like hashing of the operating system or hypervisor and try to keep those preemptions where we were taking time away from the operating system to go do measurements. We tried to keep that very short. And so by keeping it short, we could reduce the impact of these delays on the system to something that hopefully the users would not be able to notice. So that was kind of the basis of my PhD work. And along the way, we published several papers on performance aspects of this, as well as the security architecture of what we built. I also did my master's in computer science at Portland State. And before that, I actually was doing history at Lewis and Clark College here in Portland. And I did a little bit of a career change going from history to computer science once I took a little bit of a look at the job market. So I basically made that transition by kind of going down the IT path initially. So I was doing Microsoft certifications. That was enough to get me a job doing some IT support at Intel. So there we helped maintain the server environment and solve people's problems with their computers. Soon after that, I transitioned to more of an engineering role. I was kind of fortunate just to get picked up and moved over. without really having the qualifications at the time. And that's why I began the master's program around 2002 to kind of shore up my computer science background. And along the way, I was on the work side working in performance and virtualization measurement, and switched over to security about 2007, starting work on Intel's prototypes for SGX, kind of a secure place to run your software. I began my master's in 2008 and finished in 2010. And around that time, I started working a lot more on firmware. And so trying to understand how we can better secure the most privileged software that runs on your laptops or your servers, and coming up with ways that we can better armor the platforms so they're not as vulnerable to very serious vulnerabilities. And I guess because that wasn't enough, I decided to go on for a PhD, and published a few papers along the way in the area of runtime detection of rootkits, and then switched over to fuzzing firmware at work in 2016, which is going to be kind of the basis of a lot of the stuff that I'll be talking about now. And last year, I moved over to the Programmable Solutions Group to kind of form and lead the red team to go off and look at the firmware of FPGAs as well as other devices that our business group has. So if there's questions along the way, feel free to interrupt. I won't be able to see the chat, but maybe Ken can assist if there's questions.
Yeah, feel free to queue up any questions if you've got them ahead of time. If it's burning on your mind, throw it down in the chat and we'll get to it as soon as we can. And we'll leave time for raising hands and doing questions at the end as well.
Excellent. Yeah, so tonight I wanted to provide a little bit of background about software security, and kind of lead up to why we might care about fuzzing, and then do a little bit deeper dive into what is fuzzing, what are its capabilities, how might we use it, and if we were going to go build a fuzzer, and what are the ingredients that we would need in order to construct a fuzzer that would be able to go off and actually find security issues automatically. I'll introduce libfuzzer, which is an open source tool that you're free to download and try out. Kind of show a little bit of an example of how that can work with like a toy program. And then introduce some of the more advanced fuzzers that are being developed at Intel that target hypervisors, firmware, operating system, kernel code. So taking fuzzing beyond the applications that it began with and be able to apply it to lower level software on your system. And then we'll have a little bit of time for conclusions and Q&A. So just to kind of share a little bit about the background, I think this slide is probably obvious to everybody. I mean, everywhere we look today, there's software, and whether it's on our phones or whether it's running the transportation systems or our telecommunications, we're all using software in ways that we never anticipated, 10, 20 years ago. And the pace of software development is increasing rapidly. If you look at all of the GitHubs that are out there and people just writing code, but at the same time, the complexity of the software is also increasing. We have virtualization, we have firmware, we have different devices. There's a lot of different moving parts nowadays. And if there's issues in that software, then it can present actual financial, billion-dollar sometimes implications for companies or organizations, as well as we have all of our personal information, or email, or all sorts of things in your phone, and there's also safety issues. So how can we as an industry manage that complexity and reduce the risk of vulnerabilities in the software that's all around us? And if you look out, a lot of code today is written in languages that are not safe. And so there are things very regularly happening, like buffer overflows. There's people declaring arrays and copying, more than the allocated memory space of data into that array. There's integer wraparounds, where maybe you have a index variable, and with some math error, now you're improperly accessing an array in memory. There's a whole host of software issues that kind of plague software today, and firmware and hypervisors are not immune to this. So, how can we really start to try to reduce these types of issues in some of the code that's really hard to reach. And I think one of the things that always gets discussed is what is the impact of a vulnerability in software? And so in the security industry, we typically think of what's called CIA. There's confidentiality. It's, are your secrets safe if there is a vulnerability in software? As well as integrity. Could a malicious actor overwrite some of your data? And now it doesn't have the same information that you put there. And so they've kind of corrupted it. And there's also availability. And so, are you able to bring down a service like a denial of service attack due to some software vulnerability? So, with every vulnerability, it's sort of interesting to try to think about how that maps to that CIA sort of concept. And you'll find that some vulnerabilities, could impact all three, or they might just impact one of them. But it's definitely something to kind of consider as you think about, what are the implications of a given vulnerability. So how do we in the industry try to manage this complexity? So there's a lot of different approaches that get used at various organizations. One of them is code review. So if we have developers writing software, typically, there'll be a group of developers that get together and they look at the code, they try to kind of reason about it and say, why did you do it that way? And maybe, hopefully, they'll catch some vulnerabilities along that way. But, it's still a human process and humans miss things and we're all busy. And so, there's no one approach that's going to solve all of these escapes. There's also unit tests. So developers can write very targeted tests just to test out, a simple function. And just make sure that, if you give it input X, you get back output Y. And so that's, one way that you can sort of build out sort of a test framework. And there's ways to automate that. But that's, only looking at the software from a very fine-grained perspective of like a single function or a single flow. There's also regression tests. And so, running tests over time that are supposed to pass, but, maybe one day they break. And that might be able to clue you in that maybe there's a software issue. Something changed, something broke. There's a lot of work on validation. There's positive testing, trying to show that features actually work the way they say they do. And there's also negative testing of trying to break the feature. So, if there's a encryption feature in your operating system, some red team may try to break that and just try to make sure that, they're not able to break it. There's static analysis. There's tools that will run against C code on your hard drive and basically try to reason about, whether it might have a buffer overflow or whether there's certain code that's unreachable. But that's a very static way of looking at it. It doesn't actually run the code. It sort of looks at the code on the disk and tries to figure out, if there's some potential vulnerability there. So the one that I'll be talking about is fuzzing. And this is a very dynamic approach. It will actually run through the software that you want to go test. And so it takes different forms, but depending on what type of code you're running, it's very likely you'll be able to do some fuzzing, given some of the advances in the past few years of bringing fuzzing down to deeper layers of the software. So fuzzing, just to kind of level set, it's a testing technique. And the general idea is that there's some software that will create a whole bunch of different inputs. And they might be crazy inputs. It might be inputs that a human never actually would have thought of. And it'll apply it to a program. And it will really try to cause it to crash or to hang. And so the fuzzer will just keep over and over coming up with different inputs and applying it to your test program. And if it happens to crash it or hang it, it feels like that fuzzing was successful. And what we often find is that when you look at the inputs the fuzzer created, sometimes they look kind of crazy because like what human's going to think of sending like 12 pluses and a slash and all sorts of crazy characters, but often that's the kind of thing that can break the logic of some of your input parsing code. With fuzzing, there's generally two categories of fuzzers. There's guided fuzzers and there's blind fuzzers or dumb fuzzers. In the old days, fuzzing was essentially pretty dumb. Like there were software fuzzers that would just go and create all sorts of random inputs and just apply it to the code. But the problem there is they don't know what is happening with the execution of that input. And so it might be just beating its head against the door and not actually getting deeper into the program. And so in more recent years, the industry has kind of shifted to guided fuzzers. And the idea there is that the fuzzer will come up with some input, and then it'll apply that input and then observe, whether that was useful or not. And useful could mean like we were able to reach a new function that we haven't seen before, or we were able to come up with some new path through this program that has not yet been observed. And so guided fuzzers can actually be very effective in sort of automatically understanding the layout of a program and coming up with different inputs to try to work its way through different functions and come up with inputs that really maximize coverage. And ideally, you'd be able to cover every line of your program. And so that's kind of the goal of, can you get to closer to 100% coverage? It's actually hard to do in practice, but that's kind of typically kind of where we try to get to. But fuzzing, it kind of began with just working on user space applications. So just, applications running in Linux or Windows, but it wasn't really brought down to actually work on a hypervisor or on firmware. And some of the reasons why is, if you're running a test program in Linux, you don't have all the insight in what's actually happening in a hypervisor because you're at a less privileged mode. And so, how do you bring like guided fuzzing down to work on a layer that's like below what you're supposed to be able even to access? So there's been a lot of work in that area to sort of enable that. But that was kind of one of the initial challenges that had to be resolved. And so I mentioned that fuzzing is a technique to look for crashes or hangs. But like, what if you have a problem in your code that doesn't actually cause a crash or a hang? What if you just read 1 byte more than you're supposed to be reading from an array? That might not crash the program. You might get some garbage back, but there is a new technique called sanitizers, which will do runtime checking of the execution of your fuzz test cases. And if there's even like a 1 byte improper memory read or write, it would be flagged by the sanitizer because it's micro sort of checking every one of those accesses to see if it was done properly or improperly. Or there's other sanitizers you can turn on to say, if I have a signed integer, what if it wraps around because I just add one too many to that number, and now it's exceeded sort of the maximum value for that data type. And so that might just, in normal software, just cause a wraparound that might, it could cause a serious problem, or it might be something that people would just not notice because it got hidden by some other type of issue. But the sanitizers can go and catch those types of issues. The main trade-off, though, is the more sanitizers you turn on, the slower the execution of that test code becomes. Because now it has to check, 10 things at once or 20 things at once, where before you weren't doing any checking. But for fuzzing, we found it to be very effective. Just, if you're going to fuzz, you might as well turn on the sanitizers and see all the things that you're able to catch. Because often it's these very subtle things that the sanitizers are able to catch that would otherwise go unnoticed. So if we were to go and build a fuzzer, how would we do it? So essentially, there's a number of things that sort of have to happen if we're going to go create a fuzzer. The most obvious one is we need to kind of come up with some permuted data. We need some data that's, it could look like it's random data, but we need some way to sort of apply some different inputs to a program. So if we go back, in history, the early approaches, if you think of like Peach as one of the early fuzzers, they have kind of an XML-like sort of description of these of the data that you want to go fuzz, as well as the protocol. And so you basically would need to kind of define your data that you want to be fuzzed in a pretty detailed view of like what you want the fuzzer to do and how it should do it. That of course takes a lot of testers' time, and so in more recent years with AFL and libfuzzer, the more contemporary approaches are to basically automatically kind of figure out what are the data types in play and what are the flows that can happen in this program. And they use that, they work by using that guided capability of being able to observe, I've seen a new instruction pointer, or I'm seeing a new function, or if I set, these 4 bytes over here, then I reach this different part of the program. So they're always sort of refining their inputs and kind of automatically determining how to go fuzz something. So from the perspective of a fuzz tester, that makes it very easy. You don't need to spend like 2 weeks defining all the data types and all that stuff. You just say, give me some fuzz data and let's go. And so the next thing is you need to be able to start the program. And so the fuzzer has to be able to invoke your test code. And so with something like AFL, they have what's called a fork server, and that will basically kind of initialize a program up to a certain point, and then you can begin your fuzzing. And so it can just invoke your test program over and over, but not have to go through all of the initialization that would otherwise be required. You need a way to inject the permuted data into the test program. So with a lot of fuzzers, you need to write a little bit of code to say, okay, I'm going to copy this data coming from the fuzzer into these 5 variables that I want to go fuzz. And so there's a little bit of enabling that has to be done for any of these fuzz harnesses that you want to go create. And if you're going to build a guided fuzzer, because that's much more effective than a blind fuzzer, you need a way to sort of observe what's happening as you execute these fuzzed inputs. And you want to really kind of remove those inputs from your future work that are not productive. And so if you realize that setting bit 7 is never getting you anywhere, then you probably want to remove all those types of permutations from your workload because you'll just be wasting time. And fuzzers often have to deal with what are called magic constants. And this traditionally was a huge problem. The idea is that your code may have like a certain pound define, and if you don't have the right value being at some like if statement that matches what that pound define is, your function may return back. Like if you think about if there was a password, and if you don't have the right password, then you're not going to get past that part of the code. And so fuzzers, because they sort of can also operate in sort of a brute force way, it might take them years to sort of find some of these magic constants because they don't really know what they're looking for, and every input they apply gets rejected. And so a more contemporary approach is to basically trap on compare instructions. So if you look at the assembly code for an if statement, there's typically a compare instruction, and and the fuzzer is able to determine, oh, it's trying to compare this value in this register with some well-known string, that it's able to observe during compilation. And so if the fuzzer has that awareness, it can realize what it needs to provide to basically get past that ifs check. So that was kind of a revolutionary idea that helps remove one of the biggest drawbacks that there was with fuzzing previously. And fuzzers also need to keep re-invoking the test program. It's very common to do 100 or 1,000 executions a second of your test code. Just keep trying different permutations, and ideally being able to find something that causes a crash or a hang. But really, performance is key here. Like if you can only do 1 test a minute, your chances of finding things are going to be kind of low. But if you're able to do thousands a second, then you have a better shot of coming across some input that would cause some problematic behavior in your code. And the last item is when fuzzers do find problems, it's very common, at least in the older days, to get sort of bogged down with them keeping to inject inputs that kept triggering the same issue. And so you might come back after an hour and it's like, oh, I found 1 million crashes, but then it turns out they're all the same thing. And so some more of the recent fuzzers have ways to remove the redundancies, and they try to figure out, of these 1 million crashes, do they sort of bucket down into like 3 or 4 sort of actual issues? And that actually makes it much easier for a fuzz tester to go through. And that's actually an issue if you're going to deploy fuzzing like in an enterprise. You need to have a strategy for how you're going to handle redundant crashes, because otherwise, it's somebody's job to sort of wade through 1 million crashes, and nobody wants to do that. So that's actually a really key thing. Should I pause for questions, Ken, or move on a little
Yeah,
bit?
does anyone have any questions at this point? And like I said in the chat, if there's some students who are a little shy with their English, go ahead and blast us in Spanish. We've got lots of bilingual folks here. Not including me, I'm not bilingual at all. So are there any advantages? Thank you, Agustin. Are there any advantages of using an unsafe language like C, C++ instead of using other strongly typed safe languages like Java or Go?
Yeah, that's a great question. And I think we're starting to see some movement in the industry of trying out some of these safer languages like Rust. And I think that the challenge is that there's so many C programmers out there, and there's so much code that's been written in C that it's going to take a big effort to migrate a lot of that code over to something more safe. But I think we're seeing online in certain places, there are some like prototypes of taking some of the more security sensitive code and rewriting that part in Rust. And so I think what we may see is that there's certain parts of the code base that move towards a safer language first, and then we'll see what happens with the rest of the code. But there's a lot of challenges to sort of move the industry very quickly to a language that a lot of programmers of firmware or hypervisors may not be all that familiar with.
Thanks for the answer. Any other questions jumping out right there for people right now? Don't be shy. Yeah, you're welcome, Augustine. Nice question. My dad taught was count to 10. Some students are a little cautious, and then the question will come in, but it looks like that. So go ahead, Brian, and we'll.
All right,
We'll
there'll be more opportunities. Yeah.
Oh, there you go. Waiting. So thanks, Edgar. How long should a round of fuzzing take? And then we got a second question in behind that.
Sure, that's a great question. So fuzzing is never done. It's possible that the next 5 seconds of fuzzing might find the issue that you've been looking for over the past week. But that said, it becomes more and more likely that you'll be able to declare the fuzzing done based on some of the heuristics that some of these fuzzers produce. So AFL, for example, gives you a little bit of a kind of a runtime indication of how effective it's being in finding new parts of the program to explore. And so initially, when you first start fuzzing, it's probably making more rapid progress. It's finding functions it's never seen. It's making, it's traversing program sequences that have not yet been observed. But, after say like 24 hours of fuzzing, it's very possible that the progress becomes very slow. And so AFL will give you some metrics, and you'll be able to kind of conclude that, well, it's been 8 hours since it found some new path through this program. Chances are that it's maybe found what it's going to find. So you have a little bit of certainty. Well, no, I shouldn't say certainty. You have a little bit of guidance that it may be okay to halt the fuzzing. But that said, because it's non-deterministic, it's possible that just by killing the fuzzing right then, you might have missed the bug. So I guess bottom line is try to look at the heuristics to guide that decision, but there's no 100% answer.
Thanks, Brian. I pointed at the halting problem, the classic thing for computer science students to look up.
Right.
And then are there performance drawbacks? Thank you, Eduardo's this question. Are there performance drawbacks to using hypervisors or other platforms like JVM versus C++?
For fuzzing?
Yeah.
So anytime we introduce a new layer, like including hypervisors, or I'll talk about a little bit later, nested hypervisors, that does always add some additional overhead. So CPU companies try to make it as painless as possible to add those layers, but at the same time, there's just certain instructions that have to be run, and it's always going to be a little bit more overhead than just running things natively.
Another one here from Rafael. Is it better for a program to outright crash or for it to display memory leaks or other errors?
That's a great question. It's not as easy as you think it might be. I've been a member of some discussions sometimes saying, if the software is running in an airplane, what should you do if there's a crash that gets observed? you don't necessarily want to crash the plane because there was a integer wraparound. So I think it really does depend on where that software is running and what sort of assumptions there are about how robust and sort of bulletproof that software needs to be. But in general, it is safer to sort of crash, early as opposed to running in sort of a broken state. So if that's okay with the sort of usage of your device, then that may be a preference. But there's no one answer because this could also be very like a high security device that has to stay up with high availability, and then it becomes more challenging to reason about.
So why don't you continue along, Brian, and I'll try to get them to queue up the questions. Go ahead and slam them in while Brian's talking, and then we'll have them ready. Thanks, folks.
All right. So just the fuzzers basically at the root level are always creating different permutations of data to try. So if you think of like a simple C struct, in the olden days, you would have to kind of declare, here's a vendor ID, it's 4 bytes long, it's little endian, and you'd have to basically kind of spell it out for the fuzzer. And then maybe there's some sort of built-in fuzz strategy in this fuzzer where maybe 3 means it's going to alternate 1s and 0s or something like that. So that's kind of where fuzzing was, a while back, 5-10 years ago. As I mentioned with AFL, now life got a little bit easier. We can just ask the fuzzer, say, give me fuzz data for this car object, and AFL will go figure out, all the different interesting bits to go set and observe where it gets to in the program. And you didn't have to spend, a week, declaring all this stuff. And so there's a lot of things that have just made fuzzing easier to do today than it was in the past. And the way that like AFL and some of these other fuzzers work is they use genetic algorithms, and they also profile the execution. And so that means that sometimes they will splice together 2 different inputs and come up with like a third input, or they might flip certain bits of an input. And basically they have sort of a bag of tricks that they'll use, and they'll rotate around and basically come up with interesting permutations to apply to the program. And one of the most interesting things I've seen in fuzzing is this blog post here, where somebody took AFL as a fuzzer, and they said, okay, here's what I want you to go fuzz. We're going to fuzz this JPEG library. And they just gave it one file that contained the word hello. And after like several hours of execution, the fuzzer was already creating different JPEGs, and they have like kind of like different artistic styles. Like it was like, kind of mathematically looking, but basically by tracing the execution and figuring out which bytes and bits were important. Like for example, the first 2 bytes here, the fuzzer observed that if it sets them in different ways, it can get into deeper parts of the program. It starts to derive things like the file header. And then it can also eventually find its way over to a function that finalizes an image and writes it out to disk. And so if it gets there, then it's properly constructed an image. So this is an interesting link if you ever get a chance to try it out, because you'll see like the fuzzer's explorations of trying to create an actual image with only having the word hello to start with. And we don't need to obsess over these, but these are the different strategies that the fuzzer can use. A lot of things fall in the category of bit flips, or adding, subtracting different values, subbing in some known values, powers of 2, things like that. Basically, the developer at AFL did a lot of profiling and figured out like which were the flavors of permutations that seemed to be the most effective in uncovering a wide variety of issues. And it basically will just rotate around these different methods over time. And it's been quite effective. They found a whole bunch of issues along that line. And actually people are continuing to evolve like the permutation strategies and the optimization strategies for the fuzzer in different ways. And so if you take a look around, you'll find a whole bunch of different variants of AFL that all are a little bit different. Like some of them try to drive execution to a certain line of code that the developer said has changed, like maybe there was a software patch. And so there's different types of approaches, and that's kind of great for the fuzz testing community because we can leverage a lot of different tools in ways to sort of better test out our software. To talk a little bit more about that fork server ingredient, if you think about the execution of the test program, maybe it needs to read from a file, and maybe it has a bunch of stuff it has to do in the beginning. If you're going to be continually invoking that file over and over, millions of times, you might want to take some shortcuts to allow the file to properly initialize once, and then you can basically snapshot it and then basically fork all of those copies. And so at that point, the program is up and running, you're ready to provide inputs to it, and you don't need to keep reinitializing. So that's kind of one nice performance enhancement that's been added to fuzzers. And then there's compiler instrumentation. So a guided fuzzer really needs to determine how effective a given input was. And so one of the methods that is used is to recompile a program using a wrapper that goes and makes note of certain interesting locations in the code. And so one of the strategies they use is to insert basically markers at the beginning of functions, the end of functions, at different branch opportunities. And so that tells the fuzzer, if we reach some of these markers, that's kind of interesting. And so that's one of the bit of metadata that gets added in during the compilation process. And then this also allows the fuzzer to look for different traversal paths. And so if we look at this code, there's several different ways to get through it. And the fuzzer ideally would find all of them. And so the fuzzer basically creates pairs of these markers, and if it sees a new pair that it hasn't seen before, that's kind of interesting because it realizes, oh, I've found this place coming from a different location that I hadn't seen before. And so that's kind of how the fuzzer typically kind of works at runtime and tries to weed out inputs that just keep sending it down the same path. And the magic constants, like I mentioned, these were a big problem a while ago. And so there might be some code that has a magic value. And by brute force, it could take a long time to find that value. And we might never reach this code below. And so the more recent strategies are to trap on these compare instructions. So we can actually look and see what is the value we're supposed to be sending. And then we'll be able to get past this if statement. Previous to that, there was a concept called dictionaries, where the user could kind of create a text file with all of these magic numbers that might be useful to the fuzzer, and the fuzzer could pull from there as needed to see if it could sub in a value that would get it past this if condition. That works, but it's also requires more tester time, and so that's not necessarily as optimal as just trapping on instructions, on these compare instructions. And there's more advanced techniques like using symbolic execution, basically kind of SAT solvers to kind of figure out what you would need to apply to get past some of these statements. And so there's been different approaches to kind of deal with this problem over time. So just to introduce libfuzzer a little bit, this is actually a great fuzzer that if you want to start trying out one, it's pretty easy to get going with. It's built out of Clang. And essentially, I provided kind of the syntax here, how you might enable a simple file for fuzzing. And this also turns on code coverage. So you'll be able to see every line that gets executed, which is kind of useful as a sort of a heuristic. But essentially, you compile your program with this fsanitize fuzzer, and that will turn on fuzzing. And I've also turned on the address sanitizer to detect any improper memory accesses. And the fuzzer basically can save its state in a directory called a corpus. And so as you're fuzzing, it'll save all the interesting findings in this corpus directory. You can take a little break after it starts fuzzing, and then you can kind of see what it found. And then you can also run your code coverage to see exactly what happened. So here I made a very simple test code that just basically kind of compares two values, but there's actually a bug in this code. And essentially, we have a pointer here that we didn't allocate memory for. And so over here, we try to dereference it so we can write a value to it, and that would cause a crash. And we also have some code that actually probably would never get executed based on some of these settings. So this is kind of a sample example of something you can go and fuzz. And the libfuzzer is expecting this well-known function name. So you just have to create this function name. And it has a pointer to the fuzz data and then a size of the data. And then you just go and copy the data from the fuzzer into the variables that you want to make fuzzable, and then just go invoke the logic. And after a few seconds, libfuzzer was executing and it hit some different cases. And then all of a sudden it hit a crash. And it says, oh, this address points to a 0 page. And so, it's discovered that, wasn't very hard, but it discovered that crash that was in that code. And so if you want to go look at, what was the fuzzer actually, what lines did it hit and so forth, there's some kind of commands here that will show you how to create some reports. And essentially you get this back. You get a report of like the C code in general. And then you get a listing of your source code, and you can see how many times the fuzzer hit a given line. And so if there's a 0 here, that means this case was never covered by the fuzzer. And so I think we can conclude that the fuzzer always, provide at least 8 bytes, at least in the short testing, because otherwise we would have, hit this. And also it didn't hit this case here that, would not be executed. So it can be a way also to figure out, maybe there's no way for this code to be reachable too. Basically, you can get these very detailed reportings of all of the fuzzer operations and to be able to understand, how effective it was. And so you can go through that corpus directory and see what it found. It'll save all the inputs that were notable, whether they were just useful in expanding the coverage or whether they caused crashes or hangs. And it's really best to go back and keep regenerating that code coverage, because then you'll see if your fuzzing is being effective. Like you wouldn't want to get stuck, just at the first line of the code and never get past it. So by consolidating code coverage, you can basically be able to make sure that you're getting deeper into the program. So that was, kind of fuzzing 101, but like, let's say we want to go target firmware or OS drivers. What if we want to go target code that's just not like a basic application? And, fuzzing at its core, is typically forking applications. But if we're talking about kernels, can we fork a kernel? Can we fork a hypervisor? So let's review a little bit like x86 and virtualization. So when we have a kernel, that runs in ring 0, and when we have applications, those are in ring 3. And so typically fuzzers are operating in this ring 3 context. And that means that, they don't have all the visibility into the lower levels, because that's the way the system was designed. An application shouldn't be able to see the working internals of the kernel. Now, if we add virtualization to this, we can now basically take this kernel and applications and throw them into a virtual machine. And we can create another one too, and we can have a hypervisor below it to manage the whole thing. And so the hypervisor is called the VMX root, and the virtual machines are the VMX non-root, the less privileged from a virtualization perspective. And then we can even do crazy things like we can virtualize the hypervisors. And so we can take that scenario before where we had a VMX root hypervisor, and we can actually virtualize that as well. And we can create via nested virtualization a hypervisor that's below either of these two hypervisors. And so you might be starting to see there's some building blocks here for applying fuzzing to some of these OS kernels that we are trying to target, as well as for hypervisors too. Because if we have a way for the hypervisor, this L0 hypervisor, to go and inspect the memory of its less privileged guest, now we can start to do crazy things like injecting data into this hypervisor and see what happens. Or, we can go and inject data into an OS kernel and observe what happens. And so this, in order for fuzzing to work, we need to have that introspection capability. And a very basic way of doing this with virtualization is something called the MTF flag, or monitor trap flag. And basically, this will single step a virtual machine. And with every instruction, control will flow back from the virtual machine down to the hypervisor. And then the hypervisor can start taking notes about, like, well, where did I get to, in that virtual machine? And it can kind of create a log. And then it can say, okay, go run another instruction. And then the virtual machine executes another instruction. And then it automatically traps down to the hypervisor. So the hypervisor can start to build a trace of everything happening in that virtual machine. And so this works, but it's not very fast because we're always pausing the virtual machine so that we can do this record keeping. And so it's an example of, yeah, I guess we can trace what's going on in a virtual machine, but it's not going to be very fast. So can we do this better? And so one of the new techniques on Intel CPUs, I think since the 5th generation core processors, called processor trace, or PT. And so this is basically a hardware-based mechanism to trace the execution of what's happening on a system. And so if you turn it on, you can go and observe, oh, this branch was taken or not taken. Or I can filter, certain ranges of instruction pointers. So I'm only looking at what's happening in my virtual machine. So there's ways you can make this a lot faster by turning on some CPU acceleration. And so if you think about what you've seen with layering hypervisors and putting kernels inside virtual machines and having either the MTF tracing, where you single step the virtual machine, or you have Intel processor trace, you might start to conclude you have some of the building blocks for what it would take to bring fuzzing to go work on an OS kernel or even a hypervisor, or firmware as well, because there can be firmware in those virtual machines. So now we went from forking an application to now we can basically fork a whole VM. And we went from injecting fuzz data just from the command line in program arguments to now a hypervisor or an emulator can inject data into a specific address in a virtual machine that it controls. And instead of using all the compiler instrumentation, we can supplement that with Intel processor trace or MTF and basically observe, where we hit in this code that we're testing. So each of these concepts can be ported over to go work on a kernel or firmware or a hypervisor too. And so one example of this is an open source project. If you're interested in fuzzing UEFI firmware or OS kernels, you could try out KAFL. And this is one that uses processor trace, and it leverages QEMU, the emulator, and KVM for virtualization to basically run kind of a container of an OS, firmware, the device drivers, and it will use processor trace to get back the feedback to the fuzzer. And so this becomes kind of a nice way to do some testing of very privileged software just by loading up QEMU and turning on virtualization and processor trace. And then you can start to bring fuzzing to these more privileged areas of the platform. There's another one I'm really excited about called Kernel Fuzzer for Zen. It's also being developed at Intel. And this uses the Zen hypervisor as well as a very rich introspection API that can go and take a look at all the memory contents, register states. It can trace the execution. It gives you very powerful sort of like debug and triage capabilities to figure out like what went wrong, if the fuzzer found an issue. And this is actually built upon some work that one of the researchers did where they created this way to fork virtual machines, I think like thousands of times a second, which at first you're like, why do I need to do that? But then if you think about fuzzing, like, of course I need to do that because I need to inject, maybe thousands of different inputs a second into kernel code or into this firmware. And so this will basically be able to operate at very high performance and do a lot of fuzzing of very privileged software. And if you're interested in fuzzers, there's a whole variety of ones to go take a look at. I think if you're just starting, I'd recommend AFL or libfuzzer. There's also, there's the GitLab protocol fuzzer, which used to be called Peach. It's kind of interesting. And that is more of a traditional one where you need to describe sort of the data layout of what you want to go fuzz. But if you do that, sometimes it's useful because then you can specify like, well, I want you to send this message first and then that one. And so you can have ways to sort of control the execution a little bit more, and instead of just hoping that it gets automatically discovered. And so there's a whole variety of fuzzers. And I think if you've never tried out fuzzing, give it a shot, because there's a big chance you'll be able to find some very interesting issues in your code. I know every time I write some code and I fuzz it, I'm like, oh yeah, I should have thought of that. And so it's very useful in sort of detecting a variety of issues. So, it's this very powerful technique, and it's something that we can also supplement with the sanitizers. We can turn on those sanitizers and just detect all sorts of improper behaviors at runtime. It's now a technique that we can go and do ring zero fuzzing for kernels, hypervisors, and firmware. With processor trace, we can make it very fast to observe what's happening and try out more inputs in less time. And if you're writing any applications or kernel modules, I think attackers are probably going to be fuzzing them, and so you might as well fuzz them as well as a defender. Give them a shot, and it'd be interesting to see what you find. So with that, I think I'd like to thank everybody for attending. If there's questions, I'm happy to take some questions. And I put my email there in case you have more questions.
Thanks, Brian. There was a question, if you'll be able to provide us the slides later to share with
Yes, I can send those to you, yes.
Sure. I said I was pretty well 100% sure, yes, but yeah, now I'm confirming for whoever asked me earlier. Thank you.
Sure.
Good question. And then Jorge threw some links in. Awesome. I was very busy talking with Allison in private message here in the chat, talking education. It's nice to get connected. Often some of these events we find we are connected to other people, and it's great to bring these connections. And that's part of why we want to bring in Brian, and part of why Maggie's here as well. She arrived a little while ago, and thank you to Karen and Allison for some discussions in the background. I think Karen already dropped off, but she was here earlier and said hi to me. Any other questions from participants here? And a big thank you for everyone for being here. This is great.
Not, I may have two questions, but I want everybody to ask first.
Allison was telling me about the water bottle rule, which I hadn't actually heard about before. So that started our discussion. How common are rootkit attacks? Message from Raphael, question from Raphael.
Yeah, I mean, you often read about them, and they can be fairly common. It's not too hard these days for attackers to convince you to install some software that ends up providing kind of a backdoor into your operating system. And it's also one of those sort of advanced techniques that nation states use. And so there's some really interesting write-ups of like some Russian malware that was using rootkits, and some of these are very advanced, and they're hard to find because you're trying to detect them from a place that's already infected. And so that was part of the hope of the research project for my graduate school, was to be able to observe what's happening in an operating system or hypervisor from like the last remaining place that hasn't yet been compromised, like the firmware. But you might ask, are rootkits making it to firmware? And I think from time to time there are a few rootkits that are also targeting firmware. So I think it's a little bit of a law of physics that anytime there's a more privileged layer, somebody's going to go after it. And so there's definitely a lot of activity in sort of the malware community for bringing attacks down lower and lower to get more and more privileged on the system.
Yeah, thinking of Bruce Nyer, and the statement of attack only gets stronger. Great point. There's a question here from, oh, Allison, thank you. I have a slightly different take on fuzzing and the initial corpus than Brian does, and a link dropped in there as well. Thank you, Allison. Thanks for stopping by and participating as well. It's great to have some externals here.
Yeah, that kind of was going to be my question. Like, if there is any like user-friendly guide to start with fuzzing, because sometimes starting with fuzzing can be a little scary if this is the first time you're doing it.
Right. Yeah. So I think there's some great resources on the web for libfuzzer. And I can also, I think everything I show here in slides 20, in the next few slides, it should be enough to get somebody started pretty much with what's required to do fuzzing. So there's the compilation phase, and then there's this kind of special function you need to go create. And in there, it's necessary to sort of figure out what variables you want to go fuzz and make sure you start copying from the fuzz data into those variables. And then you just execute it, and you can generate the coverage using kind of this sort of syntax. So I think that's sort of like the 10,000 foot view. But I would definitely go out to libfuzzer homepage, and they have some examples and some toy programs that you can try out. But I think these instructions would hopefully get somebody pretty far along if they just want to try it out with kind of a simple program.
Backing up that fuzzer getting started tutorial is very gentle. So there's some links in the chat, and a reminder to students, and this is almost all of your courses in Zoom. There's at the chat window, there's a little 3-button menu, and you can save the chat at any time. And there's probably some good links in here that you want to save. A question from Agustin: why is fuzzing effective as an attacker? Why don't, when you don't have access to the source code, how can you derive information from whether a program crashes or not? So good basic question.
Yeah, that's a great question. And there's many ways to do fuzzing. There's live system fuzzing, where you're just working on the system itself that you're trying to test. And there's also sort of like virtualization or emulation-based approaches where you're fuzzing code inside a virtual machine. And so with the virtual machine approach, you'll typically see some sort of exception, if it causes a crash, and you'll be able to observe that. But yes, it is easier to have the source available when you're fuzzing, but it's not completely required. There's a lot of work being done for sort of black box fuzzing, where there could be tools like Ghidra, like basically disassemblers, and you can feed in binaries, and then it starts to show you the layout of that program. And even if you don't have the source code, you can kind of see, okay, well, here's the entry point, and it calls this function, and this function takes 2 parameters, and that the Ghidra tool will actually even give you a C representation back from the assembly. And so you can kind of get an understanding of what's happening in that code. So there's actually a lot of things you can do without having the source, and having a good disassembler and a debugger on hand can be very useful as you go down that path of trying to fuzz something that you don't have the source for.
Thanks for the link there, Jorge de Ghidra. And maybe one last question after this one, if someone wants to drop it in, but this one from Raphael as well. Is security through obscurity still widely used?
That's a great question.
Short answer or long answer?
Right. No, I mean, I think it still is partly used. I mean, it's not a great strategy, but I think if you go out and look at what happens in some different companies, I think there are still some companies that are still kind of going down that path where they haven't opened a lot of things, and they're just kind of hoping that nobody's looking too closely. But I think given the internet and given the increasing strength and skills of the security community, I think that's getting harder and harder to justify. So it's a much better practice to be more upfront and don't rely upon the off chance that nobody discovers how poorly designed this application was, because chances are somebody's going to come across it now. There's just too many people doing this fuzzing and security analysis.
And I think it's related to the more open and transparency in the security community. But it's still existing even in universities. They like, no, don't teach our students this stuff, because then, yeah, that kind of reaction to a lot of societal effects on this as well. I think we shouldn't teach them or else they won't attack us. And then another question from Raphael: if ring 0 is compromised, could an attacker physically damage hardware?
Potentially. Like there's some devices like flash controllers that are subject to wear out. And that is something that if they don't have wear out protection, that, you know, an attacker could keep writing and writing and writing and eventually, you know, cause some sort of denial of service by, you know, just exceeding the maximum number of writes for a given device. There are also, like, you know, technologies that allow users to customize the power draw and things like that. And so, you know, ring 0 is very powerful. And with the right device, you know, it could be possible to do, you know, some amount of damage. So it's not everything is completely fail-proof, unfortunately.
Wonderful. And thanks for the link there, Allison, as well, and contributing lots in the chat. That was great. I'd just like to really thank Brian for joining us this evening. This has been great. I'm really, really happy, and I'm happy with all the students who arrived and participated and our guests that arrived. And if you could throw up some, I think you can give some reactions, emoticons, and confetti and stuff to Brian. Hearts are good. I love hearts in my classes. Well done. Thank you so much, Brian. This has been wonderful, and I wish you a wonderful evening, and we'll be in touch more for sure.
Sounds great. And thanks everybody for all the great questions, and really enjoyed sharing this material with you, and hope to hear about some fuzzing that you do. So thanks so much.
All right. Thanks, Brian. And I'm going to stop the recording.